Okay, so today I'm talking about ants and how they relate to digitalization. So first of all, this is a little new for us at ArcelorMittal. We're one of the largest, well, we are the largest steel manufacturer in the world, over 100 million tons a year. As you've probably recently heard news, there's a lot of initiative moving forward with making green steel. So it's a bit fortuitous that Grace and Mahmoud and Michelle contacted us about 6, 8 months ago. And now we get to participate in a way to share a little bit about what we do to save energy. But I'll be honest, there are some restrictions on what I can provide. But we'll do our best to be open. So today, just very briefly, a short case study on energy savings, probably indirectly as well, some CO2. But I'm going to talk about optimization algorithms that we've implemented to schedule a galvanizing line optimally for cost savings and energy consumption. Feel free to interrupt me if you have questions, or I can field them at the end if you have them. So we have R&D centers all over the world. The topic today that I'm talking about, cost-based line programming, was developed in our Spanish lab in Avila, Spain. They have a large team, probably on the order of 20 engineers that deal with IT, IoT, and AI and all these sorts of algorithms. My role, maybe I should introduce myself. I'm a portfolio director in charge of digital manufacturing. So I oversee all the projects worldwide, make sure that our knowledge is being disseminated across all the different plants when new technologies are implemented, and to also make sure that there's a proper connection between what our plants need and what R&D is deciding to focus its activities on. So in this role, I get a line of sight to a lot of different things that are going on. But I'll be honest, my depth of knowledge in that area, in these areas, are a little less. But I'm also open to search out and find answers to any questions you might have. So the technology clip optimization I'll review today. It's been rolled out at 20 facilities worldwide in US, Canada, and Europe. Having very good value return to the business, and significantly improving how we operate our galvanizing lines. So what is a scheduling problem? And first, to know what a scheduling problem, maybe a little bit about what a galvanizing line is. So if I can, do you see my cursor? Is it showing?
Yes, we do, Mark.
Yeah,
Yes.
okay. So so at a galvanizing line, we're going to move through the process from left to right. So coils come into the line, and it's a continuous process. So you can see we have 2 coils. One comes in, and when the end gets to the welder, then we weld the next one. So this is the bottleneck of the operation, but through the rest of this line, it's continuous. It's always running 24 hours a day, hopefully. Coil after coil is being added, and what we do, so we move from the welding, we accumulate coils. So if there's some issues in the line and we need to slow down, we already have material accumulated here, and so we slow down, but we don't have to stop the line. So that's one way of managing throughput. But we clean the coil because it's dirty. It's been sitting out in the coil field. We then heat the steel up. We then dip it in a zinc pot and create a very thin layer of zinc on it. Then we may either cool it or we may anneal it again so that the zinc binds into the steel. Then we run it through a skin pass mill, which is basically like a rolling mill and gives imparts a certain surface texture that the customer wants. In addition, we remove any wave or shape going through a tension leveler. Then we may treat it with an oil or a coating that customer may want. We side trim, so customers order to a specific width. Then we pay off into a coil, wrap it, and ship it. So what you can see is a continuous process with a significant number of steps. Each one of these steps obviously prefers to run at an optimal speed or specific condition. And if the line is starting and stopping and changing speeds, then it's inefficient and energy consumption increases. In addition to just explaining what I've done, is there are other factors in play with regard to the deal, and I'll go through that in the coming. So what is scheduling? It's defining a lineup, which coils to process in which order, so that there are very few severe transitions through the line at all those different operations or steps. So which coils to process and in which order. And there are a series of rules depending on the type of steel, the thickness of the steel, the width of the steel, and the customer requirements. And so all these rules need to be followed and place the coils in the best order. Of course, this improves productivity, quality, reliability, etc. This is normally done by a person, somebody with years of experience, manually choosing coils, but what they can do is limited. And now bringing AI and algorithms into this, it allows a lot more flexibility and to be done a lot quicker. And so that's what I'll talk about. So as you can imagine, it's a huge combinatorial problem. For only 70 coils, there are billions of possibilities of what order to place these coils in. And each order has a different cost, depending on how you have to adjust the furnace, whether you have to slow down, whether the zinc coating needs to be, a certain thickness for one customer versus the other. And again, all these transitions consume either zinc for us in this process. We don't want to oversell zinc. And the transitions, furnace temperatures up and down, ramping up speeds, all consume energy. So what was developed was the clip technology, and I'll go through that. So it's a sequencing optimization problem, and the idea is to find the best sequence with the lowest cost. And ideally, lowest cost for us also refers to lowest energy consumption. We have modeling calculations to determine the sequence losses. And then we use artificial intelligence to find the best sequence. And what we use is ant colony optimization. And I'll explain using this diagram here on this slide. Essentially, what this algorithm does is if you can visualize a coil yard or all these coils, and the algorithm goes out and starts selecting various coils. And then that's the ant going out looking for food. Once it's got a lineup, it comes back and it calculates the cost for that lineup. At the same time, other ants are going out and randomly selecting other coils in a lineup and determining the cost for that lineup. And so this is happening in, multiple times per second, collecting lineups, assessing them, and determining which lineup has the lowest cost. The algorithm runs continuously, essentially until there's still some operator intervention, until the operator decides, okay, it's been running for 20 minutes. That's enough, and we'll go with this as the lowest cost option. So we've been using this algorithm for 10 years. First implementation was in 2001, and we've grown it to other types of lines, cold rolling mills, temper mills, tin lines, with great success. Many different aspects of operators knowledge are incorporated, and of course we need people from IT, PA, operations to help feed in. So some of the lessons learned, which is really what the subtask is about. Unfortunately, I just kind of read through some of this, but initially what we found was when we approached the mill and said, let's move forward with such a project, the scheduling people wanted the algorithm to do exactly what they do. And that really limits what, because what they're familiar with, it's what they're comfortable with, but it puts a significant number of constraints on what can actually be done. The computer is more powerful, it's quicker, and so it can look at a lot more, it can digest a lot more complexity. And the optimization algorithms can then make, choose the right decision. So a lot of trust had to be built, a lot of change management. But what we found was after running a pilot, getting it tuned, it was quickly realized the value it brings, making people's jobs easier, and obviously the value it brings back to the company. Not every line is the same, so there are some of those sections that I showed you in the diagram needed their own special algorithms to simplify them, but also to incorporate the important aspects of it. And that was only to improve the accuracy of the models. What else here? Yeah, barriers to overcome, like I mentioned. Another barrier we're seeing, and not just related to this, and I'll just throw it out there, is there are a lot of vendors out there, and I think there are a few on the call today. Vendors are coming to us with solutions. In fact, there's a similar type solution available that some of our lines were already using. But what we found is the combination of our knowledge of the process and our data scientists, let's say, together, we're able to find gaps in the knowledge of the vendors. The vendors know the software. They don't understand the processes as well as we do. They don't understand particularly the fine details of where our losses are. And so we were able to make algorithms, excuse me, that had a significant savings. I'm showing here, around 5 to 1 better than what vendor solutions. So if you think there's an opportunity there and you have a strong data scientist workforce and good knowledge of your process, don't be put off by what's already being used, and consider that you may be able to squeeze out more than you realize you're currently getting. So that's one obstacle, because the plan will also often say, well, we have something and we don't want to put resources towards it, and then there's a big subtle activity between research and operations to explain, well, maybe what you have is not quite the best for what you need. The solutions evolved, as I mentioned, over several years. Many new features are added, taking operator input. What would you need? What would help you make decisions? We've given you this tool, so several different, let's call apps. Apps have been made to facilitate decision making on top of our ANT algorithms. And then expanding the tool to include other facilities. So one roadblock we have now is the value is seen for a single operation, and how can we network multiple operations together, upstream and downstream? And infrastructure's coming, big data, it's coming. We're implementing it, but that's an obstacle at this point for us to expand it to a more global plant-wide optimization rather than a single facility. And I think that's my last slide. So